Hello, I'm Simone Coccia and welcome to my video abstract for my paper called Hilbert Property for integral points on affine smooth cubic surfaces, which will appear in the journal on number theory. Let's go to a presentation where I will show you the main results of my research. I will first give some basic definitions in order to state the main results of my paper. In this context, I always work with algebraic varieties defined over a number field K. And so, all the maps between algebraic varieties are meant to be defined over K. By cover of algebraic varieties, I mean a rational dominant map of finite degree. And a non-trivial cover is a cover without any rational section. Now let X be an algebraic variety defined over K, and let omega be a set of rational points contained in X. We say that omega is thin if there exist finitely many non-trivial covers, such that omega is contained in the union of the images of the rational points of the various covers. And we say that X has the Hilbert property if its set of rational points is not thin. Recently, Corvai and Zagner, in a paper called On the Hilbert Property and the Fundamental Group of Algebraic Varieties, studied the relationship between the Hilbert property and a topological property of algebraic varieties called algebraic simple connectedness. And they formulated some interesting conjectures, and they proved one of these conjectures for a quartic surface, the Fermat quartic surface, developing a new method using elliptic fibrations. In my paper, I studied an analog of their conjecture in the case of integral points, and I was able to prove the conjecture in the case of cubic surfaces using the same method that they used for the quartic surface, but in the context of integral points. So I will define what an integral point is. Let's take a projective variety x tilde and the divisor contained in x tilde. We usually denote by x the complement of d in x tilde. Then let's take a finite set of places S, which contains all the Archimedean places, and a rational point P in X is S integral with respect to D if it does not reduce to D modulo any prime outside S. Given this definition, we say that X has the integral Hilbert property if its set of S integral points with respect to the divisor D is not thin. And the analog of the conjecture of Corvai and Zagner in this case becomes the following. Suppose that X is a smooth and topologically simply connected variety defined over a number field K and such that its set of S integral points is Zariski dense. Then X has the integral Hilbert property. I studied this conjecture in the case of smooth cubic surfaces, and I was able to prove this theorem. By x tilde, we take a smooth cubic surfaces defined over a number field K, and as divisor D, I take a smooth hyperplane section of x tilde, which I call H. Then there exists a finite extension of K and a finite set of places S of this extension, such that X has the integral Hilbert property for the set of S integral points with respect to the divisor H. As you can see, this is a potential result. That is, it's possible that we have to enlarge the base field of definition of x tilde in order to have a set of S integral points which is able to give us the integral Hilbert property. So I was led to study also possible non-potential instances of this theorem, and I was able to prove that the set of integer points on the Fermat cubic surface, which you can find here displayed, form a non-thin set. The techniques used to prove this theorem are the same of the paper of Corvai and Zagner, but since we are working with integral points, there are some differences. In the paper of Corvai and Zagner, they use a method based on elliptic fibrations, with fibers given by elliptic curves with infinitely many rational points. In this case, I have conic fibrations, and the fibers are multiplicative groups with infinitely many S integral points. I hope you will read the paper and enjoy it. Thank you for watching.